Oh, for God's sake. All right, so energy, exactly what one lacks at this time of the semester. This week, this lecture, I've got 4 topics. We'll see how far we get. We've got to introduce kinetic energy, work, energy conservation, and potential energy. And hopefully understand at least some of them. It's not that bad. Don't you sigh, for realsies. Force methods took a lot of work, but you're going to find out energy is actually really straightforward if you can identify if something is moving, if something is up, if there's a force on something. I'm missing one. Moving, up, pushed, and if things are going well, I'll introduce if a spring is being compressed. That's it. That's it. That's it. That's all the forms of energy we've got. So you'll be able to put those 4 questions, one equation for each. There's one equation, one term for each, and solve for whatever you don't know. It's really not as bad as force methods. I'm going to skim over this. As I said before, energy is another way to view physics. And here are the 2 most important things about energy. Energy is conserved. Do you know what I mean by conserved? What a physicist means when he says conserved? Total amount doesn't change. Conservation to a physicist means you can, if you've got a closed system, if you've got an isolated system, to the extent where stuff isn't allowed in or out, what you start with equals what you end with. There is no change in the total. That's what conservation means. It does not mean that we better preserve what we got because it's limited. Like someone says renewable resources, not renewable resources. Oil, we should conserve electricity. They're saying we should use it carefully because it'll eventually run out. Not so with physics energy. The total amount of energy is the total amount of energy is not changing. You can't run out of energy. You can transform it into forms that are less helpful. For instance, all the chemical energy stored in all the petroleum reserves of the world. Once all that oil is burned, there's no returning it back to petroleum. So you're out of that form of initial energy. But conservation, beginning equals end. Second, energy has many forms. I just listed the 3 forms, height energy, motion energy, and we may talk about spring energy depending on how things are going. The 4th thing that I mentioned, work, is how a force, a generic force, arbitrary force, adds energy into a system. An external force can add energy into the system. There are many forms, more than that. If you understand those 3 forms plus one way a generic force can do, you're done. Okay, well, I'm going to stop telling you what I'm going to tell you. Let me just tell you. Here's your first equation of 4. Yeah, your first, really, the equation here. Kinetic energy, 1/2 mv squared, 1/2 mv squared, where v, please note, v is speed, not velocity. I mean, if you square a negative number, what do you get? Right? If you square a positive number, what do you get? So it doesn't actually matter here. But if you do have an object moving up, down, and left, right, there's no such thing as vertical energy and horizontal energy. Energy is energy is energy. Energy is scalar. It's just a number. You got 5 joules or you don't got 5 joules. There is no 5 joules northwest. I was just saying, a measure of energy, 5 joules or whatever, the unit for any kind of energy, any kind of energy, any kind of energy whatsoever is the joule. Capital J. 1 joule is equivalent to, you can break that down into kilogram, meter squared, per second squared. I'm not having you guys do a bunch of dimensional analysis. Has anybody done dimensional analysis in chemistry class? to the A's equal to B's. Okay, this can be useful if you've seen this before. You can check whether things multiply out. If you haven't seen this, I'm not going to, that's a trick, but it's not a separate requirement. I won't test you on that line. So, big thing, motion. If something is moving, it has energy equal to half mv squared. M is what? Obviously, like always. Mass, and v is, as I said, speed. Bam. Well, here we go. Let's have for equation 2. Can't do much with just kinetic energy. Boring. Force, if a force acts on an object, that force delivers energy to that object. Work is nothing but how a force energies something. Work is the transfer of energy by means of a force. Work is energy, sort of. If energy is your bank account balance, work is your paycheck or a payment that you make to somebody. Work is a transfer of energy from this to that. Does that make sense? Your paycheck is measured in dollars, your bank account measured in dollars, work is measured in dollars. Okay, now I say force times distance times cos theta. We'll talk about that in half a second. Force times distance. This is properly only true if force doesn't change as position changes. For our class, everything we're going to do, I'm going to keep a steady force. But you should know that I'm going to keep a steady force, or I'm just going to tell you the result of the work. I might give you a number, even if force is a complicated function. I would tell you the total work and allow you to do things with it. The generic form, what you could say is a varying force over a distance. Just graph it and find the area under the graph. I'm not going to give you problems where you do that. We'll apply that to find spring energy later. But you're not going to have to calculate that separately. Write it down. We'll come back to it. Okay, so the last term, cos theta. As you may have noticed, I have kept trigonometry out of this class. You doctors will be given problems where you need the cos theta. This is not teaching with trig in here. There are only trace angles, 3 angles that I will give you, and you can memorize cosine of 3 angles. And they're the easy angles. 0, 180, and 90. Okay. The meaning of the angle here is not just any old angle. There's force, there's displacement. The angle that I'm talking about is the angle between the force and the displacement. Which way is the force going? Which way is the displacement going? What's the angle between these two directions? So I'd use cos 90. Hey, what is cos 90? Do you guys know what cos 90 is? Yeah, what's the adjacent side for a 90 degree in a triangle? 90, 90, 0 triangle. Here are the 3 angles that you should know, and I'll tell you also how to avoid thinking about them. And I didn't write specifically down. Cos 0 equals 1. Cos 180 degrees equals -1. Cos 90 degrees equals 0. Yeah. Okay, here's how to think about this. If a force is in the same direction of the displacement, is it giving energy or taking energy? If I'm moving this way and somebody shoves me forward, are they giving me energy or taking energy? So if force and displacement are in the same line, if they are parallel, that work is positive or negative? Positive. I am adding energy to the system. If force is parallel, work is positive. It's just force times distance. Force times distance times 1, yeah? If force is in the opposite direction, if I'm moving this way and somebody is pushing in the opposite direction The force is slowing me down. Is that adding energy or taking away energy? Oh, come on. If I'm moving this way and somebody is opposing my motion, is that adding or taking? It's taking. So you are adding a negative quantity. Adding a negative. You are subtracting some number. I would say the work is negative. Okay, what if we talk about force at right angles? For instance, right now, as you may have heard this rumor, there is a wave force down on me. Is gravity helping me move? Is gravity propelling me along? Is gravity doing absolutely anything to my motion? No. How much energy is it delivering? Zero. Cos 90 is zero. The angle between my motion and the force is 90, so that work, that force is doing no work. The energy added by that force is zero. What if I jump up and down? Is gravity doing anything to me? Is gravity doing anything to me if I jump up and down? Yes. As I go up, is work positive or negative? Hey, yo, good morning, wake up. Hey, think about it. As I rise, as I am going this way, is work helping or hindering? Is gravity helping or hindering? Is the work positive? Is it adding energy or subtracting energy? Google form. As I rise, is work positive or negative? It would be very convenient if you would just type a plus, minus, or zero sign. Wait, crap! I didn't clear out the form. Wait. Okay. Unlink, clear, link, and save as 1112. Wait, hold on a second, cowboy. Don't. No. Okay, now you can answer. Okay. Again, as I go up, and you can think about it, or you can just read the answer on the board. As you go up, is gravity positive work or negative work? Hmm. Hmm. Again, work is positive if it's helping you. Work is negative if it's opposing you. Work is zero if the force ain't doing nothing. The correct answer is if I am going up and gravity is pulling me down, that's anti-parallel. The angle between up and down is 180, yeah? So what's cos 180? It's negative. As I rise, do I speed up or slow down? Duh, right? As I go up, I slow down. Gravity is removing my kinetic energy. As I go down, is the work done by gravity positive or negative? Positive, right? Why is it positive? I'm moving this way. Gravity is pulling this way. What's the angle between down and down? Google form, which direction? What is the angle between two things that are both pointing down? What is the angle between this direction and this direction? You could tell me parallel or perpendicular, that's not an angle. I'm telling you, you can tell me a number. As most of you have deduced, the angle between two things that are pointing the same way is zero. What's cos of 0? Is gravity giving me energy as I move down? Is gravity maybe speeding me up? Duh, right? So work is positive as you move down. Gravity does positive work as we move down, negative work as we speed up. In a bit, we're going to reinterpret the work that gravity does as, instead of an external contribution subtraction, we're going to reinterpret it as I'm storing energy in my height, or I'm subtracting energy in my height. More on that in a bit. Okay. But any force, if you know these three cosine angles, or if you have a calculator, whatever, sure, force, displacement, cos theta. Or you can just think about, is this force helping, hindering, or doing nada to my work, to my energy? Here we go. Example. Max, 15 kilos. Maya and sled, 20 kilos. Max exerts 12 newtons of force. We're going to say the snow is slippery. He's apparently wearing, what do you call those? Snow boots, whatever. He's got traction. Otherwise, he'd just be standing in place, right? We've got traction. The sled is just sliding through, as sleds are wont to do. Max pulls on the sled. It moves 25 meters. Speeds up as it goes, by the way. But my shit speeds up too fast. Whatever. You don't need to think about that. How much work does he do? Google Form C, by the way. C. The question, Daisy, is on the board, and it says Max is 15 kilos, Maya and sled are 20 kilos. Max applies 12 newtons of force, moving the sled 25 meters. Find the work he does. This is Google question C. Or is it not showing on the screen? Daisy, can you see the question on the board? Oh, okay, it is. I shouldn't let people in who are that late. Oh, whatever. My friends, all you got to do is apply to the equation. I done gave you an equation. Plug it in, baby. You got me? Thanks, Eileen. There we go. By the way, we're just being a little punk here. If I present an equation and say this is one of the core equations of these sections, write it down quickly and memorize them. There are only 4. You can memorize 4 things. Hey, I've got 2/3 of you. What about the remaining 2/3? You can do this. Third. The correct answer here, if we plug in the numbers, hey, what's cosine going to be here? Is this helping or hindering? Is Max helping the sled move, or opposing it? If he's helping, is this adding, subtracting, or what the energy? So what's cos theta? Positive, yeah, +1. Okay. The work done by Max is the force exerted by Max. The displacement of the sled is displacement of the sled. Questions about this question? The mass is irrelevant. Work, force times distance. If you know the force and you know the distance, displacement to be precise, who cares? Follow-up that you do need mass for, how fast is she going? How fast are they going? Google question D, chop, chop. A third of you did not finish multiplying two numbers in time. I'd really like it if we could participate. You can do this. Have everyone in a few minutes be able to do this. Google question D, how fast are they going? You assume that they start from rest. One more time. He does 300 joules of energy work on the sled. He adds 300 joules to her plus sled. How fast must they be moving? Apply the equation that I gave earlier. Then you add 300 joules of energy. Assume starting at rest. One more time, I'm asking for how fast. Measured in what units do we measure speed in? How fast they are moving after that much energy has been delivered. Yep, that's what I said. Their combined mass is 20. If I say the combined mass is 20 kilos, yeah, I'm talking about the sled and the sister. No, Max is 15, Maya and sled is 20. Not entire mass. Max plus sister plus sled would be 35. But I want you to think about how fast the energy delivered to the sled makes its kinetic energy. If you are confused, let me encourage you to meditate upon this. If you are not sure what to apply, think carefully about this. Here is the essence of the problem. The motion energy of an object, starting from rest, is equal to the work done on that object. If you wish to find the energy, something about Maya plus lead, apply the work done by Maya plus lead to Maya plus lead, and you'll find stuff about kinetic energy of Maya plus lead. All right, time's up. I'm going to say the correct answer is 5.5-ish. And here's how we reason about it. If I have delivered 300 joules of energy, and the only form of energy that I have mentioned or that you know about is kinetic energy, what I can say is that 300 joules equals the kinetic energy of what? Of what object carries that kinetic energy? Kinetic energy. Minus lead. Yeah. Why doesn't Max feel that energy? Because we calculated the work done on Maya, not the work done on Max. Max has two forces acting on him. There's the ground, traction, and there's the work done that he does on the sled. Sled pulls him backwards. Okay, so to solve this, I apply 20 times 1/2 is 10. I divide both sides by 10. And I undo the square by taking the square root, which is about, as I said, 5.5. 5.5.5? No, 5.5 meters per second. Is good? Okay, now let me follow this up in another thing. Max, let's go over the sled, dives aside or something. Max is a real jerk butt. And the sled goes up a ramp that turns its 5.5 meters per second vertical. How much work must gravity do to bring the sled to rest? How much work does gravity got to do to stop the sled? How much energy has it got? 300 joules. Can you find for me, if I have 300 joules of energy, the height achieved when gravity is subtracting, when gravity is removing those 300 joules? So if you go up a ramp that takes you straight vertically, actually it doesn't matter the angle, how high do you get? Apply the idea that weight is adding negative work, removing energy. How much energy? This much energy. No max. Max is let go. Just Maya and sled are going up. And this will be Joule form E. All you got to do is apply the formula here. You can do it. Let's plug in. E, what am I, yeah, E, this is E. And I'm asking for a height, not an energy. Many people are telling me how much work gravity does. I'm not asking that. I'm asking how high does she get? I told you, we discussed half a second ago, the work that gravity does is negative 300 joules. If she reaches a peak height, not moving, it means all of her energy has been subtracted off by gravity. How much work did it do? Negative 300 joules. Find the height she moved. You may round. Seriously. G is 10. One more time, I have told you the work. I am asking you to find the distance that and a force that you should be able to find exerts. One more time, the situation is as follows. She's moving at 5.5 meters per second, goes up a ramp. Assume a frictionless ramp because we ain't got friction forces. I didn't give you any information about friction. Goes up a ramp which transfers her motion to straight up. She starts at 5.5 meters per second. How high does she get? Apply the principle that gravity must do negative 300 joules of work on her if it's stopping her energy, bringing her to rest at max height. I encourage you also to think 5.5 meters per second is faster than a kid would actually run, but it's not insane. Here's 1 meter. Is it reasonable? Is it reasonable that a kid on a sled is going to go up 300 of these? Is that reasonable? How high does a kid get if you've got a red ramp or whatever? How high does a skier get? Do they get 900 feet in the air? It's not a reasonable quantity. Okay, let's do it. Which force am I asking about here? Times which distance do I have? That's what I'm asking for. Unknown. The weight of what? Maya and the sled. That's what has the 300 joules. The energy of Maya, the force on Maya. Okay, so what is the force on her? Oh, come on. Round. I don't want to divide. Yes, but bleh. Okay, so there are 200, oh, for God's sake. There are 200 newtons of force that weight is exerting. She goes the distance unknown, y, h, whatever. Now tell me about the sign of this. Is gravity helping, hindering, or doing nothing to her? Gravity is sucking energy out of her. I mean, we're subtracting kinetic energy. What about the directions? Which way does gravity point? Which way is she going? What's the angle between down and up? That's 180. You have to go 180 degrees to get from down to up. And cos of 180 is -1. So I would say 200 times y times -1 equals -300. Using advanced mathematical techniques, I can deduce that she reaches 1.5 meters height. 4 feet. Let me contrast this process with what you would have to do if you just knew about force and kinematics. The first part, to apply the first part, we would have to use F equals ma. We've got F, we've got m. We could find her acceleration. F over m is the acceleration of Maya. And to go from acceleration to velocity at the beginning of the ramp, what would we have to do? V final squared equals 0 squared plus 2a delta x. Right? That's the connection between velocity, acceleration, and distance. So I'd plug this in there. I've got delta x. I got the horizontal change. I'd find the final velocity. Okay, then I've got the velocity upward. I think the straightforwardest path to go there is to say that final velocity upward equals this, v final from before, that's a silly term to use, squared, plus 2 times -9.8 times change in height, y final. Ew, gross. If I give you a problem on a test, which I will, which connects force and acceleration and distance, force and distance and stuff, which is easier to do? Divide the energy by the force, or go through all this garbage? I don't know which method you chose, and I'm never going to ask you use only this method on an exam. So pick what is easier when it applies energy methods. Okay. I want to emphasize here now forms of energy. Kinetic energy is motion energy. If you're moving, you've got oomph. Work represents interactions. Work represents how an external force is changing your energy. There are lots of forms of, well, I'd say work is the change. There are lots of forms of energy other than kinetic. We tend to call these either potentials or internals. We'll discuss the difference between these and the general way to understand these later. But for a little while, we're just going to be talking about situations where we connect kinetic energy and the work that a simple force can deliver and so on. Then we'll start adding in different things, potentials. Okay, now I want to emphasize, here's a simple case. We're going to make it more complicated later. If you have an isolated system, something that is not touching something else, something that experiences no external forces from other objects, if there's no external force, there's no external work. If there's no external work, energy initial equals energy final. There's no change in energy. In particle physics, in the smallest scale thing, there are no other forces. There are no internal energies. So kinetic energy never changes. If you've got an isolated object, an object that has no work done. Oh my God, motion never changes if there's no external force. What law is that? That's Newton's first law, right? So the idea of conservation of energy, actually all of the energy concepts and all of Newton's laws can be connected with each other. As I said, there are two ways of viewing the same material. There. We got something god-awful now. Something really terrible. But I'm going to give you a big hint, and you can analyze this system that you could never do with force methods. I couldn't do this with, I might be able to do this given half a day and a lot of paper and a computer. I might be able to do this explicitly with force methods, but it would be disgusting. Okay, suppose I'm riding on this roller coaster. I start, okendo? I don't know that much. You start 75 feet up in the sky, 25 meters up, and you go down, and you go up, and you go down, and you do a loop-de-loop. Roller coasters work real hard to minimize friction, except at the end, if you slow down, it's breaking friction. And I will tell you that the direction of normal force is always at right angles to the direction of motion, unless you're having a really bad day. Unless what's it is lifting off the track and going somewhere else or breaking through the track. So I will give the hint that the normal force and the absent friction do no work. The only work done is that of gravity. The only work done is that of gravity. You are going up and down in different directions, but if you look at the total displacement in the vertical direction, you don't have to think about the angles. The total displacement in the vertical direction, as you go up and down, times the weight, does in fact give you the work done by gravity. I challenge thee, then, to find the speed you are moving at the top of the loop-de-loop here. If, again, you start at 25 meters height, and no, I'm not going to tell you the mass. If you are desperate for a mass, invent a mass for yourself. It cancels. Google form F, give this a shot. Work together. Again, this is F. Please put in F. What he wants us to do is find the velocity when you reach point B. Apply energy. And again, the big hint is you can totally ignore horizontal motion. Gravity only cares about the up-down. Oh my dear God. Look, I may despair from time to time about how the educational system has failed many people about preparing you mathematically for something that's supposed to be future doctors. I do not blame you if your math is behind. I do not blame you if you do not know something. But for the love of God, is it that hard to listen when I say exercise F goes in Google form F, emphasize Google form F, F, F? Following directions is driving me batty. Not all of you, not most of you. Seriously. That's how I can account for participation points. I could do the people who are here get 100% except if you piss me off by completely ignoring directions. Oh my God, it's perfect. Those who completely ignore everything get 0. Everybody did the directions. I need to think about that. Yes? Huh? Yeah. From A to B, when you are at the 3B. That says they, oh, for dog's sake, I'm sorry. What I am about to present the solution for is when you hit point B. I said A to B, and I'm sorry. Hopefully this won't be that hard to re-implement. I'm going to be a lot more heartened by correct answers if everybody is answering the same question too. Okay, and it seems that's enough. What amount of kinetic energy do we start with? Nada, zero, nichts, null, da 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 amount of kinetic energy. How do we find the amount of kinetic energy that gravity works on us with? The big hint was gravity doesn't care about the fact that you move sideways at all. Which is good because I didn't give you any horizontal distance. So if I ask, sorry for the confusion, if I ask, how much work does gravity do as I go from 25 meters high to 12 meters high? How far'd you go? Down. What's your displacement? Down. I start at 25, I end at 12. How far is it from 25 to 12? 13 meters. 25 minus 12 is 13 meters. To be precise, let's say displacement is downward, negative 13, whatever. Okay, so I go down 13 meters. I displace negative 13 meters. And I've got a weight of unknown. Uh-oh. The hint was you can make anything up. So I'm going to say that the force that gravity exerts is unknown times g. The work done by gravity is m times 10 times 13 meters. Is this work positive or negative? Is gravity helping or hindering me? Is gravity giving me energy or subtracting energy? I start at rest. Am I moving as I go down? Yeah, as I go down, I am moving faster and faster. I mean, the hint is that I pick up some motion energy. I mean, also, if you want to talk about force distance cos theta, which direction is gravity? Which direction is the displacement? You don't need to go any degrees to go from down to down. So work is 130 m. What form does this go into? What's the only form you know about? Half unknown mass times speed squared. Sweet baby Newton, I've got mass, I've got mass. I'm not Catholic, but I've got mass. Cancel, cancel. I could solve for v. I multiply both sides by 2. What is that? 260. And I square root to get v. You okay with me skipping the algebra steps there? Multiply both sides by 2 to get rid of the half, square root to get rid of the square. All right, what's root 260? 20-ish? 21-ish? Wait, really? Wait. 256 is 16. Yeah, so 260, yeah, I'd buy that. 16-ish meters per second. Hey, now follow up real fast. G, tell me about the original problem. If you did the original problem, this should be real fast. What about at the 3-meter height? What about when you're at your lowest position? You can do the exact same thing. Hint, hint, hint. Okay, la respuesta correcta, the correct answer is m times, whatever, g times, now I am changing from 25 to 3 is 22 equals half mass times this speed squared. Cancel, cancel, solve, solve. This v is roughly 21 meters per second. Is good? Capiche? Okay. Hopefully, you'll agree that this is vastly simpler than if we had to find what happens when we've got it. This is a variable acceleration speeding along. A variable acceleration, we'd have to find the area under a variable acceleration curve. Oh no, oh, you don't want to do that. That's disgusting. This energy methods can be, in general, when they apply, they aren't always useful. There will be problems that you need to do with force dynamics things. This isn't complete replacement, but it is vastly easier whenever you can apply it. Okay, and now, let me do one of your homework problems for you. How much time we got? 16:01. Shh. Stop having fun. Shh. You should be miserable. I mean, quiet. Okay. I ask you a problem in the homework quiz, whatever, about being up on a hill and rolling down to the bottom of the hill and then going partway up a hill again. 2 inclined ramps. And you don't know enough about ramps to do this with force methods anyway. So you have to use energy. I mean, that was the hint in the previous problem. We're going to do exactly the same thing as before, except now we're going to practice our principles of algebra. We're going to use letters instead of just symbols, symbols instead of just numbers everywhere. I'm going to ask trace questions. How high do you get on the other side? How fast are you moving when you reach half the initial height? How high are you when you reach half the max velocity? I want you to take 3 seconds, 30 seconds, and think about, are any of these questions something you can jump to based on what you know about conservation of energy? Or you can at least think about a method to approach. All right, I see one gimme here. As you go down, weight does work on you. And if I tell you the difference in the height, the work done by weight gives you that much motion energy. So I could find the energy given to the ball, whatever, object, as it goes down a distance h, exactly like we just did, and find its velocity down. I could then use that energy and say that that much energy is how much energy weight subtracts off me to get to my final height. Hey, if I get 70,280 joules of work done, and then I subtract 70,280 joules of work to get to my final highest point, am I higher or lower or the same height from where I started? Same height. The total amount of energy given when I go down and the total amount of energy subtracted when I go up had better darn well match. Your weight isn't changing, so the height had better be, the displacement had better be opposite. So actually, the fast way to do this, I'll show the calculation in a second, the fast way to do this is just say, how high do you reach up on the other side? H initial. Whatever H initial is, there we go. How fast are we moving when we reach, I didn't ask for the velocity, that's fine. How fast are we moving when we reach half the height? Well, in terms of what's given, I could say when I have half the height fallen down, when I've reached half the height, I have lost that. Weight has given me that much work done. Weight has delivered that much work to me. I have that much energy. H initial over 2 amount of displacement. If that all goes into my speed, then plug in exactly like we did just a second ago. So that one, I can't write down in a second, in an instant what the answer is, but the calculation is exactly what we were doing. Now the last one is a little bit more interesting, and it's what I ask on the quiz, if I recall correctly. How high are we when we reach a given speed? Now, if we are up a certain amount, that's what we want, and we're moving, we don't have all of the energy transferred into all of the work transferred into just motion energy. We're not going for just a letter that we've already got. If we start at HI, I'll answer this one first. If we start at HI and we reach some final height, which is what we're looking for, oh, for God's sake, rah, 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 rah. If we reach some, oh, for dog's sake, why you no do? Reach some final height, HF. Then I could say the work done by gravity over that time, only cares about the vertical distance, is mg, the difference in the heights. Yeah. Right? That's the work done by gravity. It's positive because down and down are the same direction. Cost of 0 is 1. This is equal to the half m. What is the velocity at this time? Vmax over 2 squared. Be careful. Vmax over 2 squared is a different number than Vmax over 2 squared or Vmax squared over 2. I am multiplying this amount of speed by itself. All right, I didn't ask this as a side issue, but how could I get the speed at the bottom? Gravity's done how much work on me? If gravity is delivered all h initial, has acted on me for a whole h initial worth of vertical distance, I could say that what? Gravity has done mg times hf distance to be, no, hold on. This is how we get Vmax, the velocity at the bottom. Vmax is not, this is not this. How I get Vmax is to insist that the speed at the bottom is equal to the total work done by gravity, bam, bam, exactly as I was doing before. Vmax equals what? 2g hf. This goes there. Solve solva. Shall I do the solve solva? I will do the solve solva. If Vmax equals root 2GHF, and I've got the equation mg HI minus HF equals half m this is HI. This is HI. HI over 2 squared. What does this become? 1/2 times mass times the square root squared becomes over 2 squared becomes, be careful if I square a fraction, both upstairs and downstairs get squared. Right? Right? What does that become? What does that become? M cancels M, G cancels G. I get HI minus HF equals 2 divided by 2 and 4. Algebra. And then to solve for HI, in terms of HF, in terms of HI, I'm going to bring HI over, quarter HI over, and throw HF over there. What's one HF? What's 1 unit of HI minus a quarter unit of HI? 1 of anything minus a quarter of it is 3/4 of it. Bam, Merry Christmas. Two steps, both of which are what we were doing the entire time here. The work done by gravity is going entirely into the energy. We plug in what the speed is given as at that height. Well, I don't know that. I didn't tell you that from the beginning. Another question I could ask on a test or whatever is to find that speed at the bottom. But we practice that as well. Speed at the bottom when I've displaced all HI is mghi. Plugga, plugga, chugga, chugga, 3/4 initial height. So actually that drawing is more or less to scale. Turn to your neighbor, discuss for 2 seconds. In H, Google form H, give me a question that I will attempt to answer real fast. And please, when you are done asking this, shh, I am going to try to address, verbal question is great. Okay, question 1, what happened to the G? There was a G on the left and a G on the right, so it canceled. No questions at this time. You don't really need to say that, but okay. Why is it HI minus HF? How far down did you go? You started HI high, you ended HF high. I mean, that's what I'm asking in terms of. So if I start up here and I end down here, I think I've gone HI minus HF distance. Shh. There are people asking. This is another way to solve speed as the previous formula? I mean, yeah, this is exactly what we did. This is the previous formula. I've only given you one kind of thing here. Why is the answer squared when solving for V max? Because half mv squared. Half mv squared is the equation for kinetic energy. How do I know when to use each equation in certain order? I apply the one and only principle. The energy given, which is for now only kinetic form, is the work done by whatever forces are stated. That's the only equation. That's the only idea. Total work gives you how much energy you were given. Bam. Can work equal kinetic energy? Yes, that's exactly what we did. Work is equal to kinetic energy. The work done by whatever forces is kinetic energy. What do these two equations you just gave apply to? Well, actually, any situation in which gravity is acting up and down. Why is it HI minus HF and not HF minus HI? Well, I was thinking about magnitudes. HI is bigger, HF is lower. Higher minus lower is a positive number. The distance gone down. If you want to talk displacement, sure, y final minus y initial. That'll be a negative number. Yeah. We're out of time. We will do the same thing for 2.5 weeks. Adios, everyone.